Morning, everybody, and welcome back to the second session of the second week. So yesterday, we started to look at the calculation of different expectation values using an ansatz for the wave function. And this ansatz was based on a set of single particle states. And since we are dealing with fermionic systems first, which in a certain sense is the most complicated case, in a certain sense. Bosons have their own complications as well. But the fact that we need to bake in the anti-symmetry in the trial wave function means that we need to pay specific attention to some aspects which deal with exactly the anti-symmetry. So yesterday we calculated the expectation value for this Slater determinant. And we wrote this determinant phi 0. So this is an ansatz for the ground state in terms of a specific operator, which we called for the anti-symmetrization operator. Or if we don't want to use that one, we can use the more compact definition, where we now have a sum over all the possible permutations which we can make. And this runs up to p factorial, which is the possible way we can permute, let's say, 3 particles, which in that case is 6, which is 3 factorial. And this is given by a -1 to the power of this number of permutations which we make, multiplied with a permutation operator. And this is again multiplied with the direct product of all the single particle states, which then define the diagonal of the Slater determinant as a matrix. And then, so these states are states which we label as a phi alpha 0, particle 1, phi alpha 1, particle 2, and all the way up to the final one, and alpha n minus 1 of x of n. And what we have done is to assume that there is a specific basis which we have chosen, which we can use as an ansatz for the lowest lying state of a system. And yesterday we looked at examples like the harmonic oscillator or atomic helium, which is one of the simplest cases we can think of, which is a 2-electron case when we freeze the atomic nucleus and the degrees of freedom which comes from that. So this normally leads to what's normally called a Bohr-Oppenheimer approximation in atomic physics. So what the case which we have is a set of single particle states. You can think of these as slots where we have a uniquely defined set of quantum numbers. And this is a kind of hierarchy which can often be motivated by our insight about a physical system. So if you're thinking of an atomic nucleus, you could think of this as all the states which are the lowest lying states in an atomic nucleus like oxygen 16. Or if you're thinking of atomic neon, the gas atomic neon, you could think of this as being the 1s, 2s, and 2p single particle states from a hydrogen type of basis. So these states all run up to the final one, which we label as an n-1. So we have n particles, which we distribute this specific way. And here, we normally define this as the Fermi level. So that's the last occupied level in this ansatz. And then we have an infinity of states above that. And then we make an ansatz for the wave function, where this basis is an eigenbasis of a one-body operator. And then we have a state j of x of I, which is again equal to some single particle energy, so multiplied with phi of j of xi. And then what we showed yesterday is that the one-body part of the Hamiltonian, which is simply the sum of these one-body operators, has this state phi 0 as an eigenstate. So what we showed yesterday, just to remind you quickly of that, is that this state or this operator acting on this specific state, this ansatz we made. And if we write out all the quantum numbers with the positions and the additional quantum numbers which we have here of alpha n minus 1, this state is actually an eigenstate of this state phi of this Hamiltonian H0. So I'm skipping all these kind of additional variables here. So the other thing which we did yesterday was actually to calculate this expectation value for a system of two particles. So when we did two particles, so for n equal 2 here, so this is just a quick reminder of what we did yesterday, then we had a phi 0 of H, the full Hamiltonian of phi 0. What we found then, if we then just fill in the two lowest lying states, which we have here, alpha 0 and alpha 1, this was given by the one body part, which is now a sum over epsilon alpha 0 plus epsilon alpha 1. And this is the expectation value for the two particle case of H0. And then we got the expectation value of the two-body operator. So we are making an assumption now that the interaction is defined by a two-body interaction. So this follows from, let's say, if you're doing a gravitational problem, it would be the gravitational force, which we assume is a two-body interaction. We have similarly the electromagnetic forces. We can have the strong forces. We can have the electroweak forces. Any kind of force which behaves as a two-body force is a typical interaction term which we can plug in. So we would then have the expectation values in terms of these integrals, and then we have V and alpha 0, alpha 1 minus, and then we have what we call the exchange term, which follows from the Pauli principle. And this is the expectation value for the two-body case of phi 0 of H of I of phi 0. So what we did was simply to write out a determinant, a 2x2 determinant, and simply spell out the different terms. And we use the symmetries, the invariance under the interchange of two particles. And then we could find that the expectation value of the interaction term is given by these two matrix elements, which we normally would bring together into just one matrix element, which we call for an anti-symmetrized matrix element. So this was basically where we ended yesterday. And one of the things which we wanted to, which we also did yesterday, was to calculate the expectation value for n general. And in that case, we looked first at phi 0 with H0. And what we found then is that this is simply the sum from over I alphas, all the possible I alphas equal alpha 0 up to alpha n minus 1, all the states which are occupied till the last single particle state. And this contains simply a sum over all the single particle energies. And we are going to use a label. So this is a lowercase epsilon. And we are going to use a label here, which is an uppercase epsilon for this ansatz. So hopefully you can see the distinction between a lowercase and uppercase here. Okay. So the other thing which we started doing yesterday was to calculate the expectation value. And I just gave you the answer. So let's now see how we get that expectation value. And we wrote this out in a more compact way. So we had n factorial, and then we had d tau, which is now the multidimensional integration elements which we have. And then we had a phi 0 complex conjugate, hi, then acting on phi 0. And sorry, not that one. Let me just rewrite it because we rewrote it yesterday in terms of this product term. And then we had A, this operator A, which we defined yesterday. And then we had A, and then phi of H. And this is something which we could rewrite as this integral over d tau. And then we have this product state of single particle states. And then we have h of I. And this is now acting on the sum over all permutations multiplied with this phi of h. So in order to gain some kind of intuition here, we did the two-particle case, which is, in a certain sense, it's a trivial case because we can actually do everything directly. But let's just, in order to gain some kind of confidence with what we are going to do here, let's look at the three-particle case, because then you can see immediately which term will appear. So let's look at three particles, and hopefully that case here, when we go through the details, is going to, be able to give you an understanding of why we get a specific final result. So in that case, we are having an interaction, which is a double sum, and it depends on particles 1, 2, and 3, and this depends on the relative distance. So I'm going to write this in a more compact way here. So I less than j, and we have just Vij. Okay? And since we have three particles and they cannot interact with themselves, this is the same as V12 plus V13 plus V23. So these are the interaction terms which we need to consider when we are setting up an integral. And then let's now just write out the Slater determinant. So what we have now is an integral dx1, dx2, dx3. And the term which we can look at first is actually this V12. So let's just pick that term. Now we have on the right-hand side from the ket side, from the bra side, we have an alpha 0 of x1. We have a phi alpha 1 of x2. And then we have a phi of alpha 3 of x3 multiplied with V12. So that depends only on particles 1 and 2. And then we have the Slater determinant, but now not the full Slater determinant because you got rid of the n factorial term. But now we are having this term here where we are looking at all the possible permutations which we can make. So let's just write them out so that we have a clear view on which terms are going to contribute. So when I write out the Slater determinant now of all these possible contractions, I will obviously have one term which goes like phi alpha 0, x1, phi alpha 1, x2, and phi alpha 3 of x3. That's the first term when you write out your determinant, a 3×3 determinant. Then we are going to have a term here which runs like minus phi alpha 0, and then I have an x1, and then a phi alpha 1 of x3, and phi alpha 2 of x2. So what I'm doing now, I'm taking the 3×3 determinant and I'm writing out the different components. And if you remember back from yesterday, we had in total 6 terms with 3 wave functions. Now, if you look at this second term here, which is actually us interchanging 2 and 3. So this is an interchange of 2 and 3 in here. And what we called it yesterday was this permutation 1, 3, 2. So we are looking at all the possible ways we can permute x1, x2, and x3 on. And there are 6 possibilities when you write out the determinant. Now, if you look at this term, what would you expect from that one? If you now think of the fact that these states are orthogonal. And we have now an integral over x1, x2, x3. And then the interaction term acts only on 1 and 2. So when you look at this integral, that means that the part with 1 and 2 here is locked because you have an interaction which depends on 1 and 2. This term here is okay because here we have 1 and 2. But then if you look at this next term from the Slater determinant, or from the determinant, has now alpha 1 with x3 and alpha 2 with x2. So that means that my integral over x3 will now involve this term here and that term here. And that is, I shouldn't say about my standard jokes, but this is the amount of money I get every time I play the lotto, 0. Okay? I never win. That's okay. I don't play either. So this term has to be 0, right? So what we will see now is of the 6 possibilities you have, there's only going to be the one where we have no permutations, which is this one, and then one other permutation. So what you will see then when you write this out, and I'm not going to harass you with writing all the terms, but I'm going to pick the one of all these 6 terms, which is going to give us something which is different from 0. So there's going to be a term now where we have, when we write out, so there are 4 more terms when we look at the permutations, and I'm going to get a phi alpha 0 of an x2. There's going to be a phi alpha 1 of x1, and there's going to be a phi alpha 2 of x3. And then we have 3 more terms, plus 3 more. Now, these other 3 more, they are very similar to this one, and they give us 0. But if you look at this one, now I have x1 and x2, which interact with that one. I have it here, and I have that part of the integral. And then there is an x3 here, which matches, so this should actually be an x2, sorry. This part here obviously matches this one and that integral. So this is a permutation which we called P213. So if you write out the determinant, the 3 by 3 determinant, you have these 6 terms, but there are only 2 which contribute. All the other ones will give you a single particle state, which is orthogonal to the one on the other side, that's on the bra side, which does not include the interaction. So this interaction here picks 2 at a time. Then you can repeat the same exercise, and then you can look at V13, and you will get a similar answer. You can do V23, and you will get a similar answer. So at the end, when you collect everything, what we are going to get is the following. So the final answer for the whole expectation value of h of I of phi 0 is in our case going to be given by a sum alpha of I. And what I'm going to do now is to write this out in a different way, because I'm going to sum freely alpha j and have a factor of a half. So if you look at your interaction term, which we put up here, we can sum it up like this, or you can put a factor of a half in front of it, and then you can sum freely, because the Pauli principle will make sure that the self-interaction terms are going to be 0. Because what you have then, with a term where you have the self-interaction, is that you will have alpha 0 and alpha 0, for instance, alpha 0, and that will just cancel that one. So you can sum freely over these terms, and what we get then is then something which runs like this. So this is going to start with alpha 0, and it's going to go up to alpha 2. So these are the states which we have. And then I will have alpha I alpha j of v alpha I alpha j minus, and then we have alpha I alpha j of v alpha j alpha I. And we write this out in a more compact way as 1/2 over alpha I, and now I just leave it unspecified, because if we have n particles, this was 3 particles, but we can just write this in terms of n particles. So this is just going to be summed up to some alpha of n minus 1. So these are the single particle states which n particle occupy. And we can write this out with this anti-symmetrized matrix element, which we discussed yesterday. And then we put an AS here to indicate that it includes the direct term and the exchange term. Okay. So if you now look at this exchange term, which we have here, and we go back to this case, which we had in the previous slide, you see now that the exchange term comes, so with direct term comes from this one, and then the exchange term for x1 and x2 comes from this term here, and that comes with a minus sign. So this is simply because we have an antisymmetric quantity, the determinant, which is a way to account for the Pauli principle. So some people would call this the Pauli principle term or just the exchange term, because you exchange 2 particles. And as we discussed yesterday, it's the same whether you interchange alpha I and alpha j here, or alpha I and alpha j in this position here. And that has to do with the fact that the Hamiltonian is invariant under the interchange of 2 particles. So this is one of the basic equations you will see again and again and again. And it's important to have an understanding where it comes from. And we're going to use that compact notation for these integrals. Any questions about this? So before we move on to second quantization, the thing I wanted to do is to take an intermediate step, because that is going to be an important step when we relate to other methods like configuration interaction theory, or mean field methods like Hartree-Fock theory and density functional theory. So in the beginning of this semester, last Thursday actually, we discussed, and you saw that in exercises as well, that we could relate a single particle basis via a unitary transformation. So if we now take the Greeks and the Latins, so we could think of having a Latin base here, which is another base, which is now given by a unitary transformation. So I'm going to stay now more with this kind of Dirac-Braquet formalism. So that means that I have a state like that, which is going to be given by a sum over all possible values lambda. And then I had an overlap coefficient, which now are the matrix elements of a unitary matrix. And this is given now by my other basis. So you could think of this as a basis, which is this lambda basis, as a basis which is handy to use. Because as we said yesterday, you can have a single particle basis, like the one which we discussed here, this one, which has analytical solutions. So the harmonic oscillator is an example. Hydrogen type basis functions are another example of that. Then you can find other basis sets, which are then the orthogonal basis as a solution to a part of the Hamiltonian. And if you look at interactions like the electromagnetic force, and you use a harmonic oscillator basis or hydrogen type of basis, you can actually find analytical expressions for many of these matrix elements, as we call them, or integrals. And that means that you don't need in many cases, to actually calculate them and have involved calculations to calculate the integrals. Because in some cases, you do actually have analytical expressions. So if that's the case, then it becomes a handy basis. And then you're going to use that basis to express another basis. And one of the exercises last week was actually to show that a Slater determinant in the new basis could be expressed by a unitary transformation times the Slater determinant in another basis. So that means that I could now actually show, so if I have this unitary transformation, I could actually show that this new Slater determinant, phi 0, in the Roman basis, so I'm going to put an I here, is related to this other basis. I'm going to write it like this, times a unitary matrix, multiplied with the basis which we had in terms of these other functions. This is one of the exercises we discussed last week. I don't know if you remember that one. But that means that we can now, when we look at these, another thing which we can show then, so this new Slater determinant, this psi 0, and let's just write it in this kind of first quantization approach first. This is going to be given by 1 over n, and this is going to have other single particle wave functions. So that will have a wave function, which I'm going to call psi I1 here, and then I have x1. I have a psi 2 of x1, where these are quantum numbers in the Latin system. And this goes all the way up to psi of n of x1. And this continues all the way up to psi 1 of xn. So these are now single particle wave functions. Psi 2 of xn of psi n of xn. Now, one thing which is important now is that this single particle basis which we have here, so this is a single particle basis. Now, the thing which is important now is that if this is an orthogonal basis and we perform this transformation, this becomes also an orthogonal basis. And that was one of the exercises last week. Now, the point now is that, however, that H0 multiplied with one of these states, I here, of xj, is not necessarily equal to an eigenvalue. So these new functions do not need to be eigenfunctions of H0. So just keep that in mind. So what we have then, we don't have a specific eigenvalue which may look like this. Okay? So that's an important thing to keep in mind. However, if you now look at this state, so one of the things which we are going to discuss when we come to Hartree-Fock theory and density functional theory is that in these theories as well, we have a single reference Slater determinant as the ansatz for the ground state. So you can have a Slater determinant given by this basis, which has this structure here. There is just one ansatz for the reference state, the ground state of the system, and we call this a reference state. Alternatively, I can assume now that there's a modified basis, which is given by this transformation here. But that Slater determinant is still just given by one Slater determinant, a reference state. So this is important. It's for something which comes later with the derivation of mean field theories. So that means that if I calculate the expectation values of psi 0 of h of psi 0, this is now going to give me a sum over all the states which we have, I equal 1 up to the final one, n. But now I'm going to have an expectation value of h0 of I. So I need to calculate an integral. And that integral may not be given by, let's say, it may not, so this I basis is not necessarily an eigenbasis of H0. And then I'm going to have plus 1/2. So the expressions looks very much like we had previously, but now we have an ij of v of ij anti-symmetrized. So if you just have one Slater determinant, like this one, the answer is going to be the same, irrespective of basis. Now, the thing which we had in the previous case was that this was just given by the eigenvalues of that specific operator, because we had chosen such a basis. If it's not, we have to calculate that integral. But still, it's just going to be a number, but it doesn't need to be an eigenvalue of the operator H. So you can still label this one as an epsilon of I. But it's not necessarily an eigenvalue of H0. Okay? So if you take a Slater determinant, whether you have a basis, a Latin basis or Roman or Greek basis, or you call your basis Peter or Pan, or whatever you call it, it's always going to give you this expression which you see here. Okay? So this becomes important now because we can relate the two expectation values with another basis. So let's assume that we fell in love with this Greek basis, because that gives us a very simple recipe to calculate the different integrals. And we want to use that one as a kind of a computational basis, as we defined earlier. But then we know that there are modifications which take place. So it's not an ideal basis. It doesn't give you that basis. That Slater determinant is not an eigen, does not form an eigenbasis of the full Hamiltonian. However, when you now look at these expressions which we put up here, theCij's, if you now look at the first term, so let's just dissect them. So we have a sum I equal 1 up to the number of particles which are present. And then we can now put in this linear combination of states. So we can then start summing over an alpha and a beta. And now we need to have a C alpha overlap. And then I have a C beta of I. And this is multiplied with the integral given by this. So what I'm doing now, I'm simply setting in the expression which you see here, and then relating the two expectation values. Now, the choice we made here is that this is an eigenbasis of H0. So in our specific case, this just results in an epsilon of alpha times delta alpha beta. So that simplifies for us. If that is the case, so that means that what we get then is a sum of I equal n, and then I have a sum of alpha, and then I'm going to have C alpha of I squared, and then I'm going to have epsilon of alpha. But you see now I need these coefficients. And theories like Hartree-Fock theories and density functional theory, they provide you with a recipe to find these coefficients through the solution of coupled nonlinear equations. So I'm just giving you the kind of overarching view on things. Then we can take the next term, which is this one. So we have psi alpha j, and then we have this integral ij, vij, and this is anti-symmetrized. And this loops over all the states which are filled by one particle. Now we can rewrite this one in terms of 1/2, and then I have a sum over ij up to n. But now I need to make a quadruple sum. And this is given by alpha, beta, gamma, delta. And I will have complex conjugate alpha of I there's a beta complex conjugate of J, and then there is a C of gamma of I, and there's a C of delta of J multiplied with the matrix element which we had originally, of V of gamma and delta anti-symmetrized. Now, as you will see later, these are calculations which we can simplify by introducing something which is called a density matrix, where we then define that in terms of these coefficients here. But that's something we will discuss later. So we're just going to leave it like that. So it means the following. If somebody gives you these coefficients and you have a simple way to calculate these integrals, then you can tabulate these integrals. And hopefully this is a basis which you have here, which gives a better approximation to the ground state of the system. So these kind of transformations are pretty common in many-body physics. And the different many-body methods, they deal actually with ways of finding these coefficients. So this is the computational aspect. You have a chosen computational basis. And then with a computational basis, hopefully then, this basis is both relevant for the physics you're studying. So if you're doing nuclear physics, the harmonic oscillator is widely used, or Wood-Saxon basis, as it's called. And then in many cases, you can pre-calculate these integrals and just tabulate them. And hopefully then this transformation gives you a better approximation to the ground state. Then you can also use this for more complicated excited states. In this course, we will mainly focus on ground state properties, okay? So this is a kind of small digression, but which you will see again and again in this course. And it links with what we discussed last week about the computational basis. The computational basis you choose is often a basis which is physically relevant and also handy from a computational point of view. Okay, so that was a small digression, and just keep this in your back burner because I'm going to bring it back again a little bit later. So now it's time to change a little bit, because when you looked at all these calculations, which we did, like the one for even for free particles, we are listing all these integrals. And the question is, do we have a simpler way of representing these quantities? And this is what is going to lead to what we call second quantization, or the number representation. So let's get a little bit started with that. So we are going to call it second quantization, or a name which I prefer is number representation / number representation. So, and we're going to focus first again on fermionic systems. So we are going to deal with fermionic systems first. And again, this is a formalism which is best adapted to situations where a single particle picture is physically relevant and makes sense. So if you're looking at strongly interacting physical systems, this kind of formalism is less relevant. So just keep that in mind, because that makes a fundamental approximation. And the way to develop your intuition now is to think of these states, which we discussed, as boxes where you can have 1 or 0 particles. So if we now look at these states, which we put up to the Fermi level, so let's do that. And then we have an infinity of more states here. And I'm going to put some labels on these states now, so which is going to make my, my labeling a little bit simpler. So I'm going to introduce a notation where I use letters like I, J, K, L for states below the Fermi level. And then I'm going to have, and the reason why, because you see that if I go along in the alphabet here, I would quickly reach I, J, K, L, and so on. But it's the reason why we often use this notation is that we deal at most with free body interactions. And then we will only need 3 letters. So in general then, however, so the states above the Fermi level are written like that. And a general state is something which I will label as P, Q, R, S, etc. That's a general state. So this is just a labeling, which I'm introducing here. Now, the thing you can do now is to think of every position here. So we would typically have number 1, 2, 3, these are just labels, up to n. And you can think of these as slots. So every one of these, so if I have a state with n particles, up to n here, 1, 2, 3, then we have a particle here, and then everywhere else up to here. So we are saying that these states have been filled with 1 particle. Now, if you have n such states, so this is the total number of states I'm dealing with, that is a truncation, because in principle, n is less than infinity. If I take the harmonic oscillators on computational basis, I have an infinity of states. So in principle then, what I'm having, if I want to express this, is a set of new boxes which run up to n. So when you see the uppercase letter n, that is my number of particles. The lowercase n is just the number of single particle slots where you can fill in an object. So all these other ones are empty. Okay. Now you see immediately now that there is a computational aspect by this. So if you have n little n slots, these are n little n bits. And if you have n particles, and normally you have n smaller or equal than n, then you can look at the combinatorics of placing all these n particles in these n little n slots. And then you would just define a word of length n, and you would fill that one with bits 0 and 1. So if we now look at the system with the 2 particles and 4 levels, so n equal 2 and little n equal to 4, the total number of arrangements you can make, and this is relevant for one of the exercises this week, exercise 2. So the number of arrangements, and this means the number of configurations. And then we're going to take a small break here after that, is equal to n of n factor, like the binomial factor. So this is n factorial of little n minus n factorial multiplied with n factorial. And in this specific case, you have, in total, you would then have 4 divided by 2 factorial, 2 factorial. So that is simply equal to, at the end, you're going to get 2 times 3 times 4 divided by 2 times 2, that one. And then you have a 2 here. So that's in total 6 states. So these are your configurations here. And if you set up these slots as boxes 1, 2, 3, 4. So we have 1, 2, 3, 4. So one possible state is this one. And you would then have a word which would be 1, 1, 0, 0. That's the way you would write it out. Another arrangement of these 6 possibilities is this one. And that would be 1, 0, 1, 0, where I start with the first bit, state 1 as the first bit, and so on. So this is the way you would now compactify your information about a given configuration. So when you see this state here, that refers to this arrangement, which, if we stick to this kind of picture, for two particles, this could be the ground state of the system. Just to give you an example. So this kind of way, this kind of bit representation of states is something which is tightly linked with second quantization. So we are going to define operators now, which create a particle in one of these slots or removes a particle in that slot. So we are going to introduce operators which remove or create, and they are normally called creation and annihilation operators. So this was just to give you the kind of, so this kind of second quantization or number representation means that we freeze out the spatial degrees of freedom. We don't deal with them, perhaps even spin, and we're only looking at how many particles are given in a certain slot, which represents additional quantum numbers. We take a small break, is that okay? 15 minutes?